Today, everybody, we have a set that contains the elements or the values of an arithmetic sequence with a common difference of 4. Now, that's not so important really, but what we want to do is show that S contains an infinite number of multiples of 17. Now, right here, let's just take a look at some elements that are in S. If n is 1, we get 19. If n is 2, we get 23. And let's hop on out here to n equals 9. Okay, 4 times 9 is 36 plus 15 is 51, and we get our first multiple of 17, namely, what is that, 3 times 17? That's 3 times 17. Now notice we missed 34, which would be the first multiple of 17, I guess, or we missed 17 because it simply wasn't big enough to be contained in this set, okay? But something to note right here is the next multiple of 17 would be 68. Now notice just by parity, 68 is not a member of S. By parity alone, without even checking the computation. Why is that? Because 68 is an even number, but members of this set have to be odd, right? Because you're an even number plus an odd number, right? And also it can be, we can show that the next multiple of 17 was 85. Is also not a member of S, right? So far, we only have one multiple of 17, and we want to show that S contains an infinite number of multiples of 17. So let's see how we might proceed. And there's more than one way, but I'm going to go modular. That's my latest favorite thing, modular arithmetic. This is equivalent to solve for n here and get some kind of congruential statement about it. When you solve a congruence equation, you're going to get another congruence. And if then that implies an infinite number just by the form, and I'll show you that. But we want to solve this equation, 4n plus 15 is congruent to 0. Another way of saying that, folks, is 17 divides 4n plus 15. Again, I like this notation because it kind of converts divisibility into a form of equality. Now, there's a result from the division algorithm. We're going to have integers x and y such that 4x plus 17y, again, the modulus right here, then the coefficient of n is what we're looking at, okay? And again, this is sometimes, I think, called, I've heard this called, believe it's called let's see, I don't even know how to pronounce it. I'll say Bezout, okay? This is the Bezout result. But it's a consequence of the Euclidean algorithm, okay? Division algorithm, just repeated over and over and over. Now, in this particular case, we can see very quickly by inspection without having to go through a formal process that x, a solution here would be x equals -4 and y equals 1. Okay, so by inspection we can do it. That's not, sometimes you can't do that, sometimes you can. For bigger numbers, it's harder to do it by inspection. But so, now, another way of stating this, by the way, and I kind of got ahead of myself, this is equivalent to saying 4x is congruent to 1 mod 17. And the reason is, folks, is you can write this piece right here, and y'all, this is getting a little sloppy, but you can write this piece is 4x is equal to 1 minus 17y. But whether it's negative or plus, this is a multiple of y. So this statement right here is absolutely equivalent to this statement. This statement, without knowing this would be the same thing as saying 4x is equal to 1 plus some multiple of 17. And we have that right here. And we actually know the values of x and y that get it done. Okay? Now, so we want to solve this. Now, what I did is I took this -4 and just substituted it right here. And this is congruent to 13. Notice that -4 is 17 away from 13. Another way of looking at that is 13 minus a -4, 17, or -4 minus 13 is -17, which is a multiple of 17. So I like working with a positive number. So we get this statement right here, which is useful because it makes these two objects multiplicative inverses, okay? Now, so let's carry on right here and see if we can solve this equation armed with this information, okay? So, in other words, 13 is the multiplicative inverse of 4, because 13 times 4 is equal to 1. Just like a pair of fractions, 2/3 times 3/2 is 1/2, is 1, right? A pair of reciprocals, the product is 1, right? So, but anyway, right here, how did this happen? How did we get from 4n plus 15 to 4n is congruent to 2? Well, notice that this is the same thing as saying 4n. Whoops, I lost my marker, it looks like. Okay, this is the same thing as saying 4n is congruent to negative 15, right? And again, my preference is to work with positive numbers, smaller positive numbers. And minus 15 and 2 are congruent mod 17. And again, it's understood we're doing modulo 17 right here. Okay, so we got to this stage right here, but we also know that 4 times 13 is congruent to 1. So if we multiply through by 13, the 4 times 13 is congruent to 1 right here, you see, folks? Okay, so we get n is congruent to 26. And I'll just be professional here. Never prided myself in being too professional, but this is mod 17 right here, okay? But now how does this prove our result? Y'all remember this is going to be equivalent to n is equal to 26 plus 17. Let's use m, but we haven't used m, right? Now, y'all, m will be an integer. M will be an integer, so you see there's an infinite number. In other words, m is an integer. There's an infinite number of integers. So any n that satisfies this condition will meet the conditions of the problem of divisibility by 17. Remember, we just found a solution to this equation right here. N is equal to 26 plus some multiple of 17, or you can just say n is congruent to 26 mod 17. All right, and so this completes the proof since there's an infinite number of integers. Okay, so QED. Now let's work just a concrete example, a simple concrete example. What if we chose n equals to 43? If m is 1, let's just off to the side here, folks. If n is, I'm trying to keep it where, yeah, there we go. Okay, if n, let's say if m is 1, okay, this implies this n right here would be what, 43? Okay, and just doing one concrete example, 26 and 17 is 43 last time I checked. Now notice that if you come up here and you take n equals to 43, you get 4 times 43 plus 15, right? Now I'm praying that that is a multiple of 17. So let's see here, 15, not praying really. But 4 times 43, this is 187, isn't it? 187? Isn't it, ladies and gentlemen? Because 4 times 43 is 160 plus 12 is 172. 172 plus 15 is 187. But this is equal to 11 times 17. Hey, what do you know? Notice that even though this is a quote arithmetic progression, it works for all integers. You can pick a negative, you can find negative multiples of 17. Anyway, the goal was to prove there was an infinite number, and we've done that. So right here, did I take the time to say, yeah, it's a QED right here, folks, because there's an infinite number of integers m. So there's an infinite number of solutions. And notice that this is not in the form right here. This is just another interesting little thing. I'm not saying that only these type of integers work. I just proved there's an infinite number of them that work. But that's not to say, you can look real quickly to note that 51, which we know is a multiple of 17, excuse me, it's clearly not congruent to 26, right? And again, we are talking mod 17, okay? So there's other multiples of 17 that don't fit this characterization. But it's still, that doesn't deflate the proof. We've proved it, as I've said, more than you want to hear. So anyway, that's all for today, folks. Thank you for viewing.